Now we go for the processes and cycle. Process is any change that a system undergoes from one equilibrium state to another state. And this process in thermodynamic will have a path. Okay, so this is change of state from 1 to 2, and this state must be connected by a process path. If no path, this is not called as the thermodynamic process. State 1 usually refers as the initial state, and state 2 also known as the final state. And the path, it could be isobaric, isometric, isothermal, and etc. And this changes from state 1 to state 2. The process happening is very slow process. Why? Because we want the changes of properties to be very uniform. And this type of process, very slow process, is also known as the quasi-static or the quasi-equilibrium process. Okay, so this is the assumption made. But usually, it's not what's happening in our practical world of engineering. Usually, for example, if we have pistons in a device, in a car engine, usually this will involving a very high speed of movement of the piston inside the cylinder. So for our analysis, for the ease of analyzing, so this is what we assume. So this is an example of the path. We have isothermal, we have isobaric, we have isochoric, and also isometric. Begin with the word of iso, meaning this one parameter speed does not change. If isothermal, P constant, isobaric, P constant, isochoric or isometric, V constant. That is for process and path. Another terminology that we could have is what we call as cycle. A cycle consists of several processes whereby the final state is being brought back to the initial state. So that is called as the cycle. Now we go for steady flow process. Steady flow process is a process whereby we don't have any changes of parameters or properties. It's always the same value at any point of time. So that is called as steady. And if the properties change with time, then it's also referred as the unsteady condition, or also often called as the transient condition. So in thermodynamics, we have a lot of flow devices. For example, we have pump, we have turbine, we have heat exchanger, we have compressor, we have nozzle. This type of devices, we always assume as steady flow. When we have a steady flow, what can be implied is that the mass in is equal to the mass out. That is called as the steady flow. Steady state, properties does not change with time. Steady flow, the mass in equal to mass out as far as the flow device is concerned and or open system is concerned. So for unsteady, the mass in is not equal to the mass out. Okay, the mass in is not equal to the mass out. This is unsteady. The mass in is not equal to the mass out. So what happened to the balance or the difference between the mass in and the mass out? The difference is being put as the left of mass inside the control volume. So if this is happening, it's very dangerous flow device right here, because if the mass in is greater than the mass out, so we have the delta M right here. So we have the delta M. So the delta M will be left inside the control volume. So we are going to have increasing of delta M upon time. Okay, upon time. So if this is a rigid tank, a very rigid control volume, what happens of the leftovers of mass inside here, it will create increase in pressure. Okay, because we are going to put mass in, always we have the difference between the mass in and the mass out. Therefore, what we have, pressure will develop, and for a certain period of time, this container will fail, or maybe it can be explode. Now we look at the temperature and the zeroth law of thermodynamics. When we have two different matters or two different body which having different temperature, and if these two body is being brought together side by side, then we are going to have heat transfer from high temperature to low temperature. This heat transfer is the transfer of energy, and this heat transfer will continue until the temperature are the same for both body, for both matters. So when this temperature are the same, then we can see that these two bodies having the same thermal equilibrium. So when there is no heat transfer, temperature are the same. So this is what being called as the zeroth law of thermodynamics. Now we go for temperature scale. We have temperature unit in degrees Celsius, in Fahrenheit, in Kelvin, and also in Rankine. But as far as the temperature scale is concerned, the temperature scale is always begin at 0 Kelvin. There's no such thing, or there's no temperature lower than 0 Kelvin. So how do we get the value of 273, which is equal to 0 Kelvin? 273 degrees C is equal to 0 Kelvin. This is what we get. This is what we do. An experiment for several gases. Then we try to increase the temperature and pressure. At different pressure, at different temperature, then we try to measure the temperature. So when we project the line of gas A, B, C, and D, when we done the experiment, and when we extrapolate the profile that we have, it will narrow down to a one value, which is equal to 0, or this value is equal to minus 273 degrees C. So that's why the absolute temperature scale in Kelvin always started at 0 Kelvin, which is equivalent to this value, minus 273 degrees C. That is the lowest temperature that we could have, okay, at 0 Kelvin. So these are some of the conversion from Kelvin to Celsius, Rankine to Fahrenheit, Rankine to Kelvin, and Fahrenheit to Celsius. For water, we also known one parameter known as the triple point. This you will learn in the pure substance topic. This is a difference in temperature. Okay, the value of delta T in Kelvin is equal to the value of delta T in Celsius. Same goes for the Rankine. Okay. Now, for example, we have two temperatures. Let's say we have T1 given in degree C, and we had T2 also given in degree C. So you want to calculate what is the delta T in Kelvin. What we do is the delta T is T2 minus T1. So when we convert T2 in Celsius plus 273 minus T1 in Celsius, convert to Kelvin, 273, then we could find here the 273 on the left is positive and this one is negative. Then what we have, this is T2 in degree C minus T1 in degree C, and this is equal to delta T in degree C. So what we have, the delta T in Kelvin is equal to the delta T in Celsius as far as the value is concerned. So if we are using the delta T in our calculation, so we don't need to add 273 at the delta T value. When you add up the 273 in the delta T value, it will give us a wrong answer. Okay.